We've reached the last of Newton's laws of motion, Newton's third law of motion. It's also known as the action-reaction law. And essentially what it says is every time you put a force on one object, it'll put a force back on you. So for every action, that's the applied force. There's an equal and opposite reaction, that's the reactive force. And what it means, again, is you cannot influence the motion of one object without having the object doing the influencing also to be influenced. So you hit a ball, the ball will actually push back on the bat. Action-reaction. While the ball receives the same force as the bat receives, the ball being lighter will experience a much greater acceleration. But for every force applied in action, the reaction is equal in magnitude but opposite in direction. Hitting a nail with a hammer demonstrates this. Here we have the hammer coming into the nail, and the hammer itself slows down on impact. This drives or pushes the nail forward. So as the nail is pushed forward, the hammer, although it doesn't necessarily bounce off the nail, is at least slowed down in its forward motion. So with any interaction, action-reaction, if you place a force on something, you yourself will be forced backward. Push on a keyboard. The keyboard pushes back on your fingers. It lets you know where you are on your keyboard. The Earth and the Moon is a great interaction system. The force of gravity from the Earth pulls on the Moon, keeping the Moon in orbit around it. But even the Earth itself wobbles due to the motion of the Moon. In fact, we can see the force of gravity from the Moon acting on the Earth in the form of tides. So action-reaction. For every force that's applied, the Sun pulls on all the planets, keeping them in circular orbits. The reaction actually makes the Sun wobble slightly from its original center of mass. If we think about this, even the most massive planet, Jupiter, is 1,000 times less massive than the Sun. So although this wiggle is detectable, the great difference in mass between the planets and the Sun means that, again, for the same force, the Earth pulls on the Sun as strong as the Sun pulls on the Earth, but the Sun is so much more massive than we are, it really doesn't change its motion very much. Action-reaction, atoms pull, or the nucleus of an atom pulls on the electrons that orbit it. Action-reaction, even the quarks, due to the strong force in the nucleus, will pull on one another. Let's talk about some fairly simple, everyday examples of how action-reaction works. Take, for instance, in sprinting, the starting block. You push backward on the block to propel yourself forward. So for every action pushing back on the block, the reaction pushes your body forward. Here is Florence Griffith Joyner at the sprint, and you notice her form is perfect. Her leg is pushing at a backward angle on the ground, pushing downward, and the reaction is that it creates a total force pushing her forward or accelerating her down the track. Her weight wants to pull her down. This downward action force on the ground creates a reaction from the force. The reaction force from the ground not only supports her against her weight pulling her down, but also creates an extra kick, creating an acceleration down the field. If you want to swim, you create an action pulling on the water, and that thrusts you forward. Okay? Your own weight displaces water. This creates Archimedes' principle, buoyancy upward. Again, action-reaction. For all the water that you push out of the way, you will get an equal and opposite force pushing you upward. Okay? And again, think about all the different strokes that you can swim. In freestyle, you normally do a front crawl where you're grabbing on the air and kicking the water to push it past you. Breaststroke, you're pulling the water around you. Butterfly, you're pulling the water past you with that stroke also. In each of these cases, you're trying to propel the water backward. That's your action. The reaction is it pushes you forward. Jumping. How do you jump? Okay? Think about this. You push down on the ground. The harder you push down on the ground, the higher you jump. Generally, athletes with more type 2 muscles are able to jump higher because they can create a larger downward force than, say, a type 1 athlete who would be better at a distance sport. Now let's use action-reaction for the whole phenomena of generating thrust. Not just with people like we've seen here. We saw how swimming we can generate thrust. We saw running, how we can create an acceleration down the track. We saw creating a downward force causes us to jump upward. But in any type of propulsion, we will see action-reaction as we force something backward, causing us to go forward. In water, we saw how when we're swimming, we're pulling the water past us. Ships are able to go forward due to a propeller, or what we call a screw, which deflects the water as it spins past it. This deflection pushes the water backward. There's your action. Stand at the back of the boat sometime, okay? And you can see the water rushing backward away from the boat. This creates the reaction, or the thrust, which propels the boat forward. Airplanes. Here, like the person swimming, there are actually a few action reactions that are taking place. You have the action from the propeller pushing the air backward. That creates a reaction which thrusts the plane in the forward direction. You have the air being pushed downward by the aerodynamic surfaces. That is an action creating an upward lift. So to go forward, you need thrust to act against the drag of the air. Okay, to do that, you push the air backward. You need lift to act against the weight downward. So you push the air downward, okay, using the aerodynamic surfaces. Action, reaction. A jet engine operates pretty much the same way as the prop plane. In the prop plane, you have an engine. The engine will basically be either an internal combustion engine or a turboprop engine. We'll talk a little bit about that in a bit. But in any case, you have the force being generated by the engine just spinning this blade and pulling the air backward. With a jet engine, we actually have the turbine blades, which are either pulling the air directly and then exhausting the air, or creating force on a turbo fan, okay, also pulling on the air. For every action pulling the air through, there's a reaction, you go forward. Here is one of the largest turbofan engines in production. This is the GE90. This is actually mounted on the 777. You can see the large turbine blades, okay? As it spins, it pulls in air, but the energy that's coming from this is actually coming from the combustion within the engines. Air is pulled in by the compressor blades, okay, which you can see from the outside is actually the large turbofan. Most of the air in a turbofan engine, about 80 to 90%, is actually diverted away from the center core. That air that comes in is compressed, it's ignited, and then the energy from the expansion of this gas turns these turbine blades, which powers the whole thing. So here we can see this jet engine pretty much acts like two engines in one. You have the large turbine blades, which act like big propeller blades. At the center, you have the jet engine itself, which is providing the power turning the whole thing. Rockets are a little bit different. Rockets, instead of pulling on air, actually generate their own thrust from expanding gases. Whereas a jet engine will pull on the existing air and push on the existing air. The rocket has its own fuel and oxidizer. It doesn't need oxygen from the atmosphere to operate like the jet engine does. And while this makes it heavier, having to carry the additional oxidizer, it allows it to operate in environments where no oxygen is present, such as space. But again, the principle is the same. We push downward on this hot expanding gas to generate upward thrust. So again, here's a, I think this is an Atlas right here. Oh, no, it says Delta. This is a Delta rocket. You can see here this small central core. If it's a Delta, it's a liquid hydrogen oxygen engine down here, and attached to it are two solid rocket boosters to give it a little extra acceleration. And the nice thing about these two, they're called GEMs, they will give it extra thrust when the rocket is full of fuel and it's having difficulty accelerating because of its very large mass. But again, rockets don't need air. They generate their own expanding gas. If we look at the combustion chamber, this is highly stylized of a rocket engine. We can imagine the hot gas pushing on all sides of the chamber at very, very high pressures. The only place where it doesn't push is where the gas is being exhausted. So basically the action is this gas gets pushed downward, and the reaction is the rocket is pushed upward. Here is the rocket engine. This is similar to the type of engine which was used on the space shuttle, and is also going to be used on the Space Launch System. And it's liquid hydrogen, liquid oxygen. When it burns, you can actually see there's almost no upright exhaust. That's very different from what we get when we look at solid rocket boosters, which have very, very bright orange flames. These hydrolox, as they call them, engines, produce very, very little noticeable emissions. It's just this, normally it's sort of a dull bluish glow that you can see, because most of the light energy is actually given off in the ultraviolet. But these are very efficient engines, and you can see that the gas is forced to expand downward, and it doesn't even flare out. The bell of these rocket engines is very precisely created such that the pressure of this gas that's leaving is actually equal to the atmospheric pressure. So they're very, very high pressure inside the combustion chamber. The bell allows it to expand, and if the pressure is too large, we get what's called overexpansion, and we actually lose some energy or efficiency because of that. If the atmospheric pressure is perfectly balanced with the pressure of the bell, we get the most efficient exhaust. Here you get under expansion. That's when the atmospheric pressure is greater than the pressure of the gas coming out of the bell. So again, we always try to get this perfect expansion. And the problem is that at sea level, what would give you an expansion like this would necessarily create this blooming of the exhaust at higher altitude as the atmospheric pressure changes. They actually tried to fix this with what's called the aerospike engine, but unfortunately, although this engine had great efficiency in terms of how the gas is expanded, it turned out to be very technically challenging and a very heavy engine, so the gains that they got from the efficiency was lost in the cost and the weight of the actual engine. It's supposed to be used on the X-33, which would have been a single stage to orbit rocket, but again, this project was eventually canceled. Now, rockets have actually been around for a very, very long time. In Asia, they developed the first solid rockets basically by wrapping gunpowder and allowing it to exhaust one end. If gunpowder is completely confined and it's lighted, it will explode. If gunpowder is just sprinkled out in the open, it just burns. If it's wrapped in this way, it creates a very directed thrust, and this became the very first rocket. It wasn't until the 1900s that the first liquid rocket was created. Solid rockets are problematic because they're hard to control once you light them. They're pretty much going to burn until the end. Whereas liquid rockets, you can increase and decrease the amount of liquid in the combustion chamber and therefore throttle them up and throttle them down. Robert Goddard was the first to successfully build an operating liquid fuel rocket, although it was kind of strange. The tank was down here and the thrust was up here. He thought it would make it more stable. It wasn't until World War II that the Germans used Goddard's invention, unfortunately, to create the V-2 rocket. But the V-2 rocket came really too late in the war to have much of an impact. It was eventually tested. The United States and the Soviet Union captured V-2 rockets, tested them in their own countries, and the inventor of the V-2, Werner von Braun, actually became one of the chief engineers for designing the Apollo Saturn V rocket. So again, liquid-propelled rockets create a downward action from very hot, expanding gas, and that creates your reaction upward. This is the Saturn V rocket, which actually had 5 F1 engines on the bottom, and this burned kerosene, and actually really refined kerosene and liquid oxygen, which is the same as the Falcon 9 rocket does today. The upper stages would actually use hydrolox, hydrogen and oxygen, liquid oxygen, because they're much more efficient at higher speeds. And here is the Saturn V rocket, the most powerful rocket ever built. And these are the F1 engines. This was not reusable. Basically, this would fall into the ocean after it was expended. And each F1 rocket motor could produce 6.77 million newtons of thrust. And 13 of these rockets were actually launched. And again, it remains the most powerful rocket ever built. It was eventually replaced by the space shuttle, which was a reusable rocket. At first, because of its reusability, everybody thought that it would be very inexpensive. It turned out to be the most complex machine ever created, with over 1 million moving parts. But I believe, forget which of the shuttles, one of the shuttles did over 30 flights. So it certainly was reusable. This is the shuttle main engine, and again you can see it's burning liquid hydrogen and liquid oxygen. Almost no exhaust is visible except for this shock cone down here. But again, you can see the fog from the condensation. The liquid oxygen and liquid hydrogen are very, very cold. The shuttle also used solid rocket boosters. Again, once these are lit, they cannot be throttled up or down. However, solid rocket boosters are nice because it can generate a very large amount of lift, very large amount of thrust, I should say, at the beginning of a rocket's trajectory when it's fully loaded with fuel, and it can be very, very heavy. The solid rocket boosters would separate after they burned out, and the shuttle would continue with an external tank and only its main engines going. Now, ion engines sound like something out of science fiction, and we'll hear them in science fiction quite a bit. But ion engines are actually real engines where we use electric fields instead of chemical reactions to accelerate the thrust backward. Now, unfortunately, they don't generate very much thrust. They don't generate a lot of force. But they can generate thrust at a very efficient manner and can be solar powered. You can control the electric field or energize the electric field with solar panels, and basically just use some type of propellant, such as xenon gas, as your gas that you're accelerating. And this accelerates it to very, very high velocities, giving it quite a bit of thrust. Space Launch System is basically how the United States is trying to go back to the moon. It looks like a hybrid of both the Saturn V that originally took us to the moon and the space shuttle. In many ways, it has a lot of similar traits to it. The first launch was planned for 2018, is yet to launch, probably next year. The second launch was supposed to take a probe to Europa in 2022. I think that's been extended to 2024. Also, the third launch has now become the second launch. In any case, like the space shuttle, it has two boosters. These are actually 20% bigger than what was on the space shuttle. Instead of an external tank being attached to the rocket, it has this large tank which is attached to 4 shuttle engines. Unfortunately, this is not reusable, so it's going to fall into the ocean. And then at the top, you have upper stages which propel a Orion capsule. So the core of it is basically, very much like a space shuttle external engine. Has space shuttle engines on the bottom of it, has the space shuttle boosters, but the Orion capsule is very much like what we used with the Apollo capsules. And again, the core stage has 4 of these RS-25 engines. These are the engines, some of them actually flew on shuttles, will be reused for this purpose. And each engine produces about 1.8 to 2.3 million units of force, so a little bit less than the amount of force that we got from the F-1 on the Apollo missions. So instead of 5, it has 4, and that's why the external boosters are needed, because the rocket engines themselves will be more efficient than the F-1 engines, but they're basically going to require an additional push when they're leaving the pad. And here's one of the solid rocket boosters actually being tested on the ground. Again, here's the first version. We call that Block 1 that's going to go up. Later versions that will go to the moon would be the 1B block, and you can see it's a little bit bigger because the upper stage is a little bit larger, more powerful. And then you have cargo, Block 1B and cargo Block 2 for larger and larger payloads. So this is supposed to be one of the avenues that we're going to get things into orbit, and eventually possibly send a crew to Mars. Of course, Elon Musk has been doing very, very well with his Falcon rockets. This is the original Falcon 1, now the Falcon 9 Heavy is his most powerful rocket that he has. But his intention is to actually retire the Falcon 9 and eventually replace it with, here's when he put one of his Tesla cars in orbit, eventually replace this with he originally called it the Big Falcon rocket, but now he's calling it Starship. And it's actually changed a little bit since this diagram right here, but that's a current rocket that he's working on. And again, this sort of compares different versions that we've seen so far. Here's ESA, the European Space Agency, its rocket. It is able to take a payload of 21,000 kilograms into orbit. Compare that to the Falcon 9, which has a payload capacity of 22.8. This is not reusable, this is. So again, SpaceX has been able to take quite a bit of satellite business away from both the ESA and also from Russia. This is their Proton rocket. So each of these carries about the same amount. The cost for the Proton's a little bit more than Falcon 9. The cost for the ESA rocket is significantly more. This is the Delta IV Heavy. Carries a little more payload than the others, but it also tends to be more costly than all the other options. So this is being retired and will eventually be replaced with the Vulcan rocket. This is Blue Origin. This is Jeff Bezos' rocket. We don't know much about it because he's very secretive. We don't know how much it's going to cost. It's said to be able to take 45,000 kilograms into orbit, but again, they're so secretive about this, we really don't know much about this. Here's the Falcon 9 in its heavy configuration, able to take 63,000 kilograms into orbit. So this has been used a few times to carry heavier satellites for military payloads. Here's the Space Launch System, which will eventually be able to take over 130,000 kilograms into orbit in its largest configuration. SpaceX is hoping to be able to launch 250,000 kilograms into orbit. That would be a upscale from their original rocket by a factor of more than 10. But again, this is still in development, and sometimes he has success, sometimes he doesn't. And again, comparing this to the original Saturn V, the Saturn V was able to take 140,000 kilograms into orbit. Again, another comparison, okay, just showing the different rockets that have been available.